Hey everyone, how's it going? We're going to be taking a look today at the concepts review that we've set up for your AP review session for Calculus BC. So we're going to get started right here. This is for sections 1.2 through 1.6 in your calculus book. Okay, so here we go with your review. The first things that you guys looked at in calculus was just kind of a review on functions. So chapter 1 deals with functions and their graphical characteristics. To facilitate the study of functions, it's important to visualize mentally the graph of a function when given algebraic description. So really the first thing here that you need to do is be familiar with a lot of the parent functions that you learned all the way algebra 1, algebra 2, geometry, pre-calculus. So pause it right here. We'll take a quick preview of these and then try to graph all of these functions, okay? And then when I get back, we'll take a look at what I did. Don't forget, you're supposed to label your axes. So label your axes, okay? Right, so pause it right here. Clearly, there's a bunch of different ways that you can label your axes here. I'm just going to go ahead for this one and just say 1, which would mean that each one of those lines is a unit of 1. I'll put a 1 up here also so that we can see it's the same scale on the y-axis. This is y equals x squared, which you should be really familiar with. That is a parabola, and it looks like this. Okay. Number 2, x cubed. Again, label the axes 1 and 1. Oops, got my 1 in the wrong place. And a couple of important points, 3 in this case. And here is the shape of a cubic function. All right. The absolute value function has a shape that looks like a V. So we're going to draw our V. The important part of the V is to figure out where the vertex is. And since there's no translations on this vertex, we're going to 0, 0, put our one big point there, and then set up our V. Oops. So there's our first row. Let's get down to the second row. Sine of x. You're going to have to do a little bit more work on this one. So I'm going to make this positive 1 and negative 1 over here. And then let's make this pi, which would make this one pi halves, negative pi halves, etc., etc. And let's remember, for the sine function, we start, sine of 0 is 0, sine of pi is 1, sine of negative pi is negative 1, and then sine of 2 pi is 0 again. So we're drawing that familiar sine shape. And this is just meant to be a review, so you should be able to graph these pretty easily by now. Cosine x is a lot like sine x. Make that pi over 2, and we'll make this 1 up here, and we won't make too much of a fuss here. Pi over 2, this is pi, so cosine of pi is 0. And then, no, messed that up now, didn't I? Cosine of pi is negative 1. Here's our wave. And that's just reminding me that I did that first one wrong for sine. So let's get rid of this sine curve. I don't know what I did or why I did it that way. Foolish for area, foolish moves. Sine of pi is 0. Pi halves is 1 and -1. So here, let's take this slow. And on this side, there we go. Okay, so now all of you have been twitching at me. I don't blame you, actually. All right, same scaling here, pi halves and 1. And we'll, over here, at pi halves, well, tangent is sine over cosine, and cosine of pi halves is 0. So that means that we have vertical asymptotes here at pi halves. At pi over 4, the tangent is 1 and -1 on the other side. So we get a graph that looks remarkably like this. And then, of course, the next period looks exactly the same way. And then we're going to be stuck with half a period over here on this side. Here's the next period for tangent on the left. Then that half period over there. So how are you all doing? Did you get the first 2 lines pretty well done? Well, I made a mistake, so I don't imagine that you made a mistake now, did you? Let's do the next set. Secant. Now, secant is 1 over cosine. So anytime cosine is equal to 0, you're going to get a vertical asymptote. So cosine is 0 at pi halves, and all multiples thereof, or all odd multiples thereof. So it looks like we're going to have basically the same asymptotes that you would get from the tangent function, which makes sense because tangent is also has a cosine on the denominator. Okay, so for the cosine function, you'll probably remember that for, the secant function, you get graphs that kind of, they're not parabolas because the range is wrong, but they do look like a U. And over here, you get that half. So here's our secant. 2 to the x, let's do that one. 2 to the x when x equals 0. 2 to the x equals 1. When x equals 2, 2 to the x equals 4. So that's already off of the charts over here. 1, 2, 3, 4 would be right about here. So 2 to the x looks similar to this. Exponential growth, they all have the same shape. They all have that ski jump shape, as I like to say. Okay, now log base 2x. Let's remember a few things about log base 2x. First of all, if y is equal to log base 2 of x, that means that 2 to the x power equals y. Okay, so when x is no, when 2 to the y power is equal to x. Okay. So when x equals 0, well, there's no way that 2 to the y power would ever equal 0. But we know that as x approaches 0, that y power is going to go to negative infinity. Now, when x equals 1, 2 to the 0 power is 1. So when x equals 1, y is equal to 0. So we get this. Again, that is asymptotic. Okay. And then when x equals 2, okay, so you got 2 to the first power equals 2. So when the x-coordinate is 2, the y-coordinate is 1. So that creates that graph. Remember, for all logarithmic functions, the range is from 0 to positive infinity, non-inclusive of 0, of course. And I meant the domain is from 0 to positive infinity. The range is from negative infinity to positive infinity. Okay. It'll get there, but it'll get there really slow. All right. You could do the exact same thing for any base. Just remember that when you get the x-coordinate is equal to the base, the y-coordinate is going to be equal to 1. So log base 5, or since we have it here, log base 4 would have the y-coordinate at 1. Log base 3 means x is 3 and y is 1, but they all go through this point, 1, 0. Okay, 1 over x, that it looks like a, how do I say this? It kind of looks like a hyperbola with the x-axis and the y-axis as your asymptotes. Apparently, I'm not very good at drawing this one. And you could argue that I'm not very good at drawing any of these, but, and I wouldn't say you're wrong. All right, so here we go. I forgot to do axes and label. Okay, that takes care of 1 over x. Square root of x, we all know that. That is going to be half of a parabola that is sideways. So this goes through the point 1, 1 and through the point 4, 2 when x equals 4, y is equal to 2, and it also goes through 0, 0. So here is that half of a sideways parabola. And finally, this last one, a squared minus x squared square root of. If you recognize that as a circle, then you, my friend, are well on your way to success. Let's see, that is a. This is going to be the top half of the circle because it's a positive square root. And it's not going to actually look, oh, no, that's kind of looking like a circle. There we go. More or less. So that takes care of all of the functions, if I remember this correctly. Yeah, that's all of our functions. Let's see what comes next. Okay, so answer the following questions about the indicated functions. In completing the table below, you may use the following abbreviations. R is a set of real numbers, and I would love it if all of you watching would use that double-stemmed R for real numbers. That's what they tend to use at the university level anyways. J is a set of integers. Again, a double-stemmed J for integers. N for natural numbers, and that is a double-stemmed N as well. This exercise may be done as the appropriate sections of Chapter 1 are completed, so take a minute here, pause it. You may need more than a minute, but go through all of these and pause it, come back with answers. So maybe the thing that you should do here is just start talking about all the domains. I think that's easiest first. So domain answers the question, what numbers can I substitute into the function? So for the x squared function, I can substitute everything. X cubed, likewise, there's no x that I can't substitute. Cube root or absolute value of x, everything. Sine of x, that famously goes all the way across the x-axis, as does cosine. Now here's where we run into some problems. So this is all the real numbers except for when x is the odd multiples of pi. So how do I get an odd multiple? That is 2n plus 1 times pi, except, and this is the same, all real numbers except where x equals the odd multiples of pi. 2 to the x, all real numbers. Log base 2 of x, we talked about that one now, didn't we? Log base 2 of x only has positive, positive domain. So x needs to be greater than 0. And if you want to write this in set notation, you could absolutely write it like that. 1 over x, this is all real numbers except when x equals 0. And then square root of x, same thing, except for the square root of x, you can put in 0. And then for this circle, x has to be between negative a, and a. Now the question is, can I substitute a? And the answer is yes, you can. So we get brackets on that one. So that's all of our domains. Let's start looking at the ranges next. All right, let's get to the ranges. For x squared, all the y coordinates have to be positive, so the y goes from 0 to infinity. For x cubed, I think y can be all real numbers, yeah, because it has that shape like that. Absolute value, again, the y coordinate can only take on positive values, including 0. Sine, this is an interesting one. For sine, the y coordinates oscillate between negative 1 and 1. So all the numbers in between negative 1 and 1 only. You'll never get something larger than that. Likewise for cosine. Tangent. Tangent goes all the way from positive infinity to negative infinity as well. We may have some breaks in the curve, but the y coordinates always go to infinity. So this is all real numbers as well. Now secant is a really interesting one because, sure, the only place where we don't get a y coordinate is between negative 1 and 1. So we need to have a set that includes all positive numbers from positive 1 to positive infinity and from negative infinity to negative 1. So that looks like negative infinity to negative 1, bracket, union with 1 to positive infinity. They don't really give you a whole lot of room to write here, do they? 2 to the x, those are only positive results. I think you saw from the equation that they were just a ski slope, or ski slope, whatever. So that is, well, no, the only controversy here is, can y actually equal 0? Is there an x that I can substitute here so that 2 to the x is equal to 0? And the answer is no. So for the range, y must be between 0 and infinity, not including 0. Log 2x. Now for this one, the y coordinate can be everything. So even though our domain is restricted to positive values of x, our range is going to be all real numbers. Same thing with 1 over x, all real numbers. Square root of x, you might remember that is only positive half of the parabola that this comes from. So y should be between 0 and positive infinity. And then over here, the y coordinates also go only for that top half of that circle from which this curve comes from. So y can only be between 0 and a, inclusive. Okay. So that takes care of all of the ranges. I tend to find that that's the ones that students have the most problems with. So we're going to continue. We're going to do the rest of the whole line for all of these. And pause it here. Let's try A through D. Pause. Okay. Zeros. When is x squared equal to 0? Well, that happens when x equals 0. Is there symmetry to the y-axis? Yeah, y-axis. Y equals 0. Is this even or odd? Well, the left side looks just like the right side, so that is an even function. Is it periodic? No, this doesn't repeat. Is it one-to-one? Yes. For every x value, there is only one y value. Oh, I'm sorry. No. I'm just reading this again. For every y value, there are two x values for it, so no over here. So a one-to-one function would look like that, which is conveniently the next one that we have over here. This is a one-to-one function. So for every y value, there is only one x value that goes with it. Let's go back to the beginning of this. The zeros, that happens when x equals 0. Is there symmetry? Yes, there is. If you look at the top, if you take the graph and you rotate it 180 degrees, you would get the exact same curve again. So when you can rotate 180 degrees, maybe I should say pi radians, but when you can rotate pi radians and the graph stays the same, you say that you have symmetry about the origin. Is this even or odd? Well, the functions that have symmetry to the origin are odd functions by definition. Is a function periodic? No, the shape never repeats itself. Absolute value of x, this has a 0 when x equals 0. Symmetry, is it symmetric to, why did I say that? It's symmetric to the y-axis. So this has y-axis symmetry. And I see I'm making a mistake here. The equation of the y-axis is x equals 0. Why did you let me continue? Is this even or odd? The left side looks just like the right side, so this is an even function. Is the function periodic? No. Is there one-to-one? No. One-to-one, you might want to think about that as the horizontal line test. So this fails the horizontal line test, so no. Sine. Zeros happen at every multiple of pi. Every whole multiple of pi. There you go. Symmetry, this is symmetric about the origin. It's an odd function. Maybe I should have been consistent and said x equals 0. Let's do that. Is this even? Is this odd? Guess what? It is odd. And I think that if you have gotten to chapter 9 and you saw that the sine function were only odd powers and odd factorials, you can kind of understand where that comes from. Is a function periodic? Yes. The period repeats. The period length is 2 pi. Does this pass a horizontal line test? No, it doesn't. Similarly, cosine doesn't. It also has a period of 2 pi. This one is an even function, which means that it's symmetric about x equals 0. And these zeros happen on the odd multiples of pi over 2. So this is 2n plus 1, which is my odd number generator, over 2 multiplied by pi, which means more mistakes here. This one is symmetric about the origin. How about tangent? Tangent has zeros at all of the multiples of pi. So that is n pi. It is symmetric about the it's symmetric about the origin, which means, again, if you rotate it around the origin 180 degrees, you would get the same function. So this has origin symmetry, which means it's an odd function. Is this periodic? Yes. The period of this one is pi. Is this one-to-one? No. It does not pass the horizontal line test. You can imagine drawing a horizontal line. You would cross through multiple tangent x's. Okay. About halfway done with this. Secant, this is just like the reciprocal of cosine. It is a reciprocal of cosine. What am I saying? So the reciprocal of cosine is never equal to 0. Does this have symmetry? And yeah, it has y-axis symmetry. So it's symmetric around x equals 0, which makes it an even function. How often does this repeat? Just like cosine, the secant function will repeat every 2 pi. Does this pass the horizontal line test? No, it does not. 2 to the x. Is this ever equal to 0? No. Is this symmetric? No. Is this odd or even? Neither. No symmetry here. What is a period? Nope. And does this pass the horizontal line test? Yes, it does. Gosh, I hope I remembered all of that in order. Log base 2, you can imagine this is very similar, but this one does have a 0. This has a 0 when x equals 1, because 2 to the first power equals 0. Does this have symmetry? No, no symmetry, which means it's neither even nor odd. And it doesn't have a period, nothing repeats. Does this is it one-to-one? Does it pass the horizontal line test? And yes, it does, if you think back to that graph that we had. Let's go to 1 over x. Does 1 over x equals 0? No, never. Does this have symmetry? And yeah, this one does, because if you rotated this one, the quadrant 1 would look just like quadrant 3. I mix up my quadrants all the time. So yes, it does. It has origin symmetry. Is this odd or is this even? Neither. That means it doesn't have a period either. No, I'm sorry, those two are not linked. Does this have a one-to-one correspondence? I'm thinking about that horizontal line, and yeah, it does. This brings us to our last two. When is this function equal to 0? Well, it's equal to 0 when x equals 0. Does it exhibit any symmetry? No. Is it odd or even? Neither. Does it have a period? No. Does this pass the horizontal line test? And although the range is not all real numbers, it does pass the horizontal line test. So yes on this one too. Last one here. When is this half circle equals 0? Well, that happens when x is positive or negative a. Does this have symmetry? Yes. It has symmetry about the y-axis. Does this have a period? I'm forgetting what this next one was. Is this odd or even? Neither. Period? None. And does this is this a one-to-one function? Does it pass the horizontal line test? No, no it doesn't. Man, that was a lot of stuff. But we're not finished. Is there a relationship between symmetry and a function's graph and the symmetry in the function's graph and the function being odd and even? Yes, there is. So even functions are symmetric about the y-axis, whereas odd functions are exhibit origin symmetry. It doesn't work the other way around necessarily, but it does work this way around. So, finishing up here, hopefully finishing up, let's see. Now we got a couple more. Draw the reflection of cosine x through the x-axis. So if we reflect cosine x about the x-axis, you know, where we once had y-coordinate of 1, now we have a y-coordinate of -1. And at our pi halves, those are still 0. So basically, we're drawing the cosine function upside down. Do that a little bit carefully. I don't think I was careful enough. So there is the reflection of the cosine curve around the x-axis. Looks like the camel's back, don't it? How about 2 to the x? This one will be a little bit easier. When x equals 0, 2 to the x equals 1. So this one is going to do one of these things. And then how about x minus 1? Well, first of all, maybe we should draw square root of x minus 1. When x equals 1, y equals 0. When x equals 2, y equals 1, etc., etc. I think this is y equals root x minus 1. And typical me, I did forget the scaling here, so I should do that. Okay, if I want to reflect this gray curve around the x-axis, all I got to do is zoom, 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 right? There we go. Reflected around the x-axis. Draw a reflection about the y-axis. Oh, okay, well, this is interesting as well. The cosine curve exhibits, or it is an even function. So if you try to reflect this about the y-axis, you're basically going to get a cosine curve. Not basically, you are going to get a cosine curve. So draw the cosine curve. And yeah, I did mess that up. Hey, delete. There we go. And down here, and then down here, and then over there. Okay. There's a cosine curve. It's actually pretty sloppy, but you know, we've been at this for about half an hour now. How about 2 to the x? So around 2 to the x, we're going to go backwards. This is on the y-axis, so it's still going to be the same. We're going to go to infinity on the left side, and we're going to go to 0 on the right side. Okay. And, oh, I messed that up. That's b. And then for c, let's remember again what that square root function looks like. We just did that, so that's easy. What does that look like reflected about the y-axis? Well, there we go. Reflected about the y-axis. So that takes care of that first one, guys. Hopefully you enjoyed that. That was rather long. They're not going to go this long, I promise you. Not everyone is this intense. So hopefully you saw that this was a long exercise, not particularly difficult. Not until the very end yesterday or of the assignment, which required a little bit of mental gymnastics. So we'll see you next time for our next calculus review. Maybe we'll get some actual calculus.